Yep, over to you, Bankang.
Hey, welcome everyone. Thank you for coming to this session. So this session will be about rethinking the world computer paradigm with array programming language. We are very happy to have Juuso come here and give a talk about this. So I'm not gonna say any more things. So without further ado, let's welcome Juuso.
Right. Let me share the screen. Cool. You all see it?
Yep, clear.
Great. So yeah, hello everyone. And today I'm going to present some of my work in research at the University of Oxford. And I guess this talk is a little bit more, it's more like holistic view of my research and where I want to go with it. The actual things that I research here are more particular to array programming languages. But back there on the background, there's like a bigger idea about how new programming languages could be created and what some features that I would personally want to see in those programming languages are. So I usually like to start the talk with just talking about what and why I'm doing this. So rather than hiding the information somewhere down further into the presentation, I rather give it right at the start. So my general view and maybe the overarching theme that I want to insist today is that I think that programming has this disconnect between communication and compute or computing, in the sense that when I then study sometimes I also tell that I study implicit parallelization. So what this actually is, it's made of two components. First one is compute, and nowadays it's many times the question about how we can use multi-core systems efficiently. So some ways to approach that are type systems, parallel programming, GPUs, and array programming languages. And I want to think these as a tools really to address this challenge of computation on current day hardware. But then as I started to study more about the compute problem, I started to realize that there's maybe even a bigger challenge here, which is that about the communication. So the communication would be then how in a distributed network are the nodes connected to each other, and how we can query this information and the capabilities, and something that are constraints, as we will later see. So some ways to model these networks is then like systems theory, and some category theory can be mixed up in there. And then more particularly, I've been working on a lot with NixOS, which I will present some ideas that NixOS has in compared to other Linux operating systems and why it's useful. And then finally, the SMT solvers also integrate to this, but it uses information from NixOS to really do the distribution for us. So the question here is really about scheduling. And for me, when I'm talking about compute and array programming languages, what we are really doing is that we are scheduling array operations to a distributed network. And the Ethereum is more like, this is the stuff that you know, but the thing that I'm very interested in Ethereum is this idea of an abstracted programming paradigm. So when you write smart contracts, one of the very nice ideas and some very novel idea I think that Ethereum really brought forward is this concept that the developer just writes their code, but they don't have to care about where it runs. So the infrastructure is abstracted from them, so that you don't really know which computer runs this off your smart contract, and you don't really have to care either. You just push it to the code and it runs somewhere. And very nice thing is that in Ethereum, they not only get this infrastructure abstraction, but also some guarantees about the proper execution of the smart contract. And what I've been then researching is that how could this be incorporated into a general purpose language? And this now connects to the maybe what in Ethereum was initially the idea of the world computer, but it got kind of like tossed away, and they focused more on smart contracts instead. And the way I've kind of like ran into this programming language stuff is quite complex or convoluted, let's say, is that I started from telecommunications. And then the problems that I ran into when doing telecommunications pushed me to programming languages. You might sometimes also hear this if you've been listening to maybe, I think Solana founders were also coming from telecom. So this is not completely one of exception that I somehow started in telecommunications and ran into Ethereum and distributed networks and programming languages. And the connect here is that if you think about it, this 5G mobile networks and what we call beyond, so talking about sixth generation cellular networks are similar to Ethereum in the sense that both are distributed and both share a vision of the world computer, which is this a network of composable computing. So in 5G, it's called edge computing. And the idea is basically that these smaller handheld devices do computation on other devices. And one example of this is Huawei's so-called Da Vinci project. And here, what Huawei is trying to do is having like, if I have a phone and you have a phone, then my phone could somehow loan the computation power from your device to achieve some capabilities. Another example could be these AR glasses. So you might know that, or the concept of that you have some very lightweight hardware, and then it uses the computation through the cellular link. So it goes through the telecom mast or the base station, and the servers are on that base station. So it's a way also for telecom operators and companies like Huawei, which actually produce the base stations which you use to connect to devices, and doing the phone to have this integrated computation offloading paradigm. So the kind of like another way to say is that if you think about phones from Apple and others, I think what the Huawei's like point here was that, well, they don't even have to compete, and they maybe cannot compete with Apple's hardware, but because Huawei also does the base stations, they can compete with these features that they can source from the network to give capabilities and functionality to the end user devices that are not just possible on like hardware or like a phones that are created by a single company which does not control also the cellular network. And yeah, one of the kind of like interesting thing here is that Huawei's size of this global network is quite big. Whereas with Ethereum, you have the same idea on an abstract sense, that you have the storage and compute which come from the validators or the node runners, to which you pay in the form of transaction fees. And the network is much smaller, because if you look at Ether nodes, you see that there's like 7.5 thousand execution layer nodes in the world, and that's not quite much. So I think in general, I think this concept of going towards offloaded computing is quite prevalent in nowadays computer networks. And then I like to talk about what's the next big score in programming languages. Maybe you read the Big Score book. It's very nice. You should probably check it out. But basically, it talks about these ideas which seem quite prevalent going forward. So my take on this is that in the context of programming languages, the next step is a programming language which can kind of like facilitate the creation of this new kind of app store for general purpose computing. And if you want to put your tinfoil hat on top of your head and think about maybe the reasons why Huawei might have been banned in the US, is probably a bit connected into the App Store ideology, in the sense that if you think about US companies, well, they have Apple, which has the App Store, and then they have Google, which has the Google Play Store. So in some sense, the US can kind of like control nowadays that what goes into your phone. But with 5G and this kind of like low latency computing, there comes this paradigm shift in which the control moves from the hardware producers more to the people or the company which controls the network. Or this is at least kind of like this threat model that can exist. And I also like looked into this and studied this before getting into programming languages. And in general, you can think that there's two main challenges in this computation offloading paradigm, which I've marked here as 1 and 2. So the first is that if I have a phone and you have a phone, then if you are going to do some computation for me, you probably want to ensure that whatever I run on your phone doesn't hack your device or your bigger server. So this is the point 1. And there's some ways to address this. And usually, I think there's the Golem network is one example in Ethereum, which tries to, which has attempted this notion of a general purpose computing on top of Ethereum. And there the idea was sandboxing. So you take something like a Docker container, and then you run the software inside of this sandbox to ensure that that basically you couldn't hack the device or something like that. But then there's also another properties that are quite relevant, such that whether the program that I give to you ever terminates. So this very, very foundational problem in computer science of the halting problem is also kind of like relevant here, because in general, when you have some program that your device runs, you cannot know beforehand whether it will ever end. And this is one of the guarantees that in this edge computing computational offloading paradigm you should have. And another thing is then the challenge on me now, that now if I provided these guarantees for you, that it's fine to take programs from me and execute them, then what about that if I cannot know, or if I cannot do the computation like what is 1 + 1, how can I guarantee that when you give me the response, you just don't give me a 0? Because by the basis of the fact that I'm asking you to do some computation for me, it implies that I, for some reason, cannot do it. And this is like prevalent in you could think about the AR glasses now, the augmented reality glasses, that if they want to do some computation and now you just return me like 0 values, then these very lightweight hardware constrained devices cannot really verify whether that computation was done properly or not. And here it's kind of like, this is usually where some like Golem network and most of these current approaches break up, or kind of like they kind of like are unable to solve this second problem, which is then ensuring that the computation is indeed right. And I don't really have better solution to this than game theoretical guarantees. But then thinking from the point of view of a programming language, what this means is that if you would want to somehow be able to address both the first and the second point, the programming language should have distribution built into it, or this concept of program slicing. So somehow I should be able to take my program and then me personally be able to slice it into smaller pieces for the distribution of using multiple devices. But on the other hand, if you can do the distribution, then it also implies that you could maybe overlap the results a little bit to see if like most of the nodes which does the computation for me agree on the results, then maybe it's a good enough model to trust. And then I ran into these array programming languages to address this, because these languages are constrained very foundationally, because the only data type that is allowed is this rank polymorphic array. And it makes reasoning about programs and things like termination much easier, because the recursion and the for loops are actually in they're structural. So it means that it's bounded by the data type. So by banning the user to write their own for loops or if or else, or like any source of randomness, you can actually prove that certain array programs terminate. So you can kind of like have these guarantees that you want, but it's not solving the halting problem. It's kind of like going around it and finding ways to make the language so constrained that these static properties and information can be inferred from the user's program. But then this also connects to this bigger idea that where I want to really go towards to, is that instead of the programmer describing how to execute some program, the infrastructure works as this lens which chooses the nodes and ways to slice the program for you. So this also is very relevant, that if you now have different devices and you have to figure out which one you want to do the computation on, somehow the infrastructure should be making the decisions for you. Otherwise, it's kind of like it's not much out from current cloud computing paradigm. And I want to kind of like solve this, how I got here through some projects which I've done before, to really like insist on the fact that I like suddenly didn't just, there was some red thread, or how they say it in English, but basically I did these different demos and eventually ran into this problem of which I then started to solve with array programming languages, static semantics, SMT solvers. So I want to show you a few demos which might help you to understand where I'm coming from. And yeah, this first one is this vacuum cleaner thingy. And this was quite long ago, but here down below, you can see the vacuum cleaner. And what it will do for me is that it will use this server on my desktop PC to do leg detection for me. So let me just show you the video. And the point is that here you can see my legs as I move in the room, and the vacuum cleaner is following me, but the computation to really figure out, or the computation really happens on the PC. The vacuum cleaner is just a dumb device which is loaning the compute power from the PC. I don't know, maybe there was a pass-through of the voice here from the video, but basically at the end I could ask the vacuum cleaner where I was going, or where I was in the room, and the vacuum cleaner would use the computation from the PC to do the computation. So that was the concept of compute offloading. That was what I started with, the computation part. But then the next thing was this augmented reality tablet, which I created as a custom hardware. So here I created this tablet, like an augmented reality tablet through which you can look at things by pointing it to different IoT devices. So when I was pointing at that particular wall, the device would show me controls for lights. And now that I point the TV, I can stop the kind of like the seeking of the video. And then I put my lights off switch on the other wall. So these would use kind of like, again, information collected before to achieve features that were not previously possible. And yeah, that was that. But the point here was that I very early now saw that the problem here is really about communication. It's not only that whether you can compute, whether your vacuum cleaner can kind of like offload the computation to some other device. The next step is then be able to somehow communicate with these IoT devices, know the address at which the lights are, the IoT lights are, or where the Apple TV is to control it. And this kind of like connects now into the 5G thing, which I did next. So I moved this thing into the 5G network because in a 5G network, when your phone has an internet connection, it implies that the base station knows where your device is, like physically, but also its IP address. So 5G networks were kind of like an ISPs, like internet service providers in general, have information about the infrastructure because they know the addresses of these devices. So in a 5G network, you could, in a very, very kind of like a subtle way, integrate the compute and communication onto a single distributed network. And then as I was kind of like then figuring out that, oh, how do I create an app store on top of this? Then I kind of like got into the array programming languages because of the issues 1 and 2 from this slide. So that then drew me into array programming languages. And then I did something called static semantics of APL, which is about the formal proofs part of the first problem. So that's how I then started to go deeper into programming language theory. And then that wasn't just quite enough for me. I also took SMT solvers to do scheduling for me. So now that I could verify that my programs are correct, then the second problem is then to use the infrastructure somehow to select the nodes on which the computation is actually happening on. And my solution to this was NixOS. And NixOS basically, it kind of like works as a telecom service in the sense that you don't have to be an ISP because NixOS is able to integrate the compute and communication into a single infrastructure. So NixOS can tell you where your device is in a programmatic manner. And now combining all of this stuff together, we can get into the idea of a smart language, which would be the implicit parallelization of these array operations or big-N operations that use SMT solvers that integrate with NixOS infrastructure. So very long way to really explain how I got here. And a nice way, or something that I want to kind of like you to think about this concept of a lens. So lens is a view into a data structure. Like at least this is how it's usually described in category theory. But you can also think about the lens as a way to look at your infrastructure and do the node selection for you. And it will be an essential notion going forward in these slides, because it works as this driving force to model these distributed networks for us. And yeah, so then if you want to get more theoretical, it represents this bi-directional stateful computation, which is able to not only view data or have a partial view, but also write to it. So in NixOS, you could say that creating an OS image is this identity arrow, or it could be. It's not really an identity arrow, but the idea is that basically when you compose something with a NixOS, it gives you also all the required information to recreate the operating system from the start. So in some sense, you are able to go back in the state to recreate your operating system. And this is actually the thing which now makes possible to create these composable networks with NixOS. And in BQN, you also have a lens, which is represented in this operation of under, or a donut. So yeah, I have one example in BQN, which uses this donut thingy. I don't want to go too much into this, but the idea is that in a lens, you can take some representation of data and kind of like reformat in a way that you want to be the output. So here, BQN is read from right to left. So this is the shape, or the kind of like the data format you want, and this is the data you actually have. And this under operation, or this lens, what it actually does is that it figures magically the way to represent the underlying data structure in a new format. And that can be a little bit hard to understand, or maybe grasp the idea from that operation alone. So now I'm going to bring that to more into the NixOS part of it. So basically, NixOS is a way to combine the computing and communication in a single package. So if you compare it to something like Docker, you could say that Docker only provides computing for you, or something like a Kubernetes. It only does the compute for you, but it doesn't really handle the networking between those Kubernetes nodes. And that's in a retrospect to something like Tailscale. And Tailscale only provides communication, but it doesn't provide the compute or computing on those nodes. So you kind of like have this awkward situation in which to have a distributed infrastructure, you kind of like have to take these two parts and make them work together instead of it being a single thing. So in this sense, the NixOS makes the Linux configuration into Legos via this concept of flakes. So flakes is just an interface to compose these different NixOS configurations together. And what the NixOS does is that it allows you to compute a fixed point of multiple NixOS servers on evaluation as a single infrastructure. So this is a way you can like take multiple server configurations, but when you are computing the NixOS declaration, which defines the whole operating system, you can already at that point integrate the parameters from one computer to the another. And one way to like solve this is that I can ask that how and what software is running on my Linux operating system. So this command here gives us a graph of all of the software installed on the NixOS server, or the image of some node that we have. And the point is that basically this is useful in the sense that if I would have my device and you have your device, this way I could check whether you have the required software to even run my program. And where this meets Ethereum is then this project called Homestaker OS, which is actually a project of my company to manage Ethereum nodes. And there's a website for it, but then also we have our own validator infrastructure as an NixOS configuration available publicly. And we also received initial funding from Ethereum Foundation to drive this thing forward. But what this really does is that this now ties us back to the 5G networks and figuring out what's the address of our device. So we can run this command here, and it will give us the address on which the Lighthouse endpoint is in our VPN network. But the thing to notice here is that I just ran this on my developer machine. And my developer machine is not part of my validator cluster in the sense that I don't do validations on my laptop. But I can still query information from this NixOS declaration. So it allows these dynamic environments to build on different devices and various toolings on top of it. So if we now think about the lens again, what really happens is that my laptop is using a lens provided by NixOS to look or have a view into the infrastructure from which I extract information and integrate tools on top of. So in NixOS, you can also have something like direnv, which means that when you actually go to the folder of your project, you are giving a project-specific lens into the infrastructure. So this provides us the necessary computable or programmatic tooling to query our distributed infrastructure and the nodes in it. And this can be done automatically and on project basis. So actually, you can even run this command, given that you have Nix installed, and you would get the same result. But you don't have the same lens as I do into the infrastructure, because you will only have the read-only access, whereas I will actually have the kind of like these access controls to really reach to these servers. But another thing that is very fancy is that we can use this to query information like what's the current block in Ethereum right now. And I can run it like this, and then I will get a long answer, which is like cropped here. But the basic idea is that this allows tooling to be created on top of this lens, which provide useful tools for me without really relying on any third party like a service provider to fetch the information. So this is like a quality of life improvement for developers, but on the other hand, what this is really doing is that this is solving the networking, the communication part of a distributed computation infrastructure on top of which we could create the programming languages on top of. So that's why I find it interesting, is that when the complete server configurations can be public, like we have in GitHub, anyone can go see it, and we are encrypting parts of the VPN configuration, so you cannot really see what's going on, or you cannot connect, like anyone just cannot use our servers. But what it does is that it also helps others to replicate our distributed infrastructures. So it's like a next step into the kind of like the transparency of distributed networks, in the sense that now if you think about Ethereum, you don't really know how different people are configuring their infrastructures, but this allows someone to take our configuration and recreate for them. And then the interesting part then it comes that you could also, if you think about this, like there's not that much in between to actually start integrating different networks together by doing like, if you have one network and I have one network, we could use this same concept of a lens to give a partial information of our infrastructure and share our resources this way. So it not only bridges the gap between the third-party service providers, but it also gives us these new ways to model our networks. And yeah, the lens concept is very strong here, because we can represent partial information which is enforced by access control layers to share our infrastructure, our distributed infrastructure running at our home or maybe some cloud computing service between each other. And then something that is kind of like interesting is that it goes back to these constraints. So access control layer is one form of constraint. And then we can see that these constraints now start to integrate with something called SMT solvers. So if you think about SMT solvers are AI, but AI is more than machine learning. Nowadays, everyone is talking about ChatGPT, and that's only machine learning part of the AI. But you could think about combining constraints as a way to also inhibit artificial intelligence in the form of emergent properties. So before we had the vacuum cleaner, you could tell the vacuum cleaner that in order to function, it has to charge. So that's a constraint that the device has. But then there could also be the optimization part of this problem. So the vacuum cleaner could be told that the objective is to collect as much dust as possible. And this could be like arbitrary objectives that you give to the vacuum cleaner. But the point is that once you kind of like pile onto these constraints of different systems, you can start to see maybe like an observer might think that this is an intelligent form of thinking, because now the robot vacuum cleaner might tell you, it might decline your request to clean your room because it has to charge. But on the other hand, it might also prioritize some other room to clean before it goes to your room to clean it up. And another example is from this paper I wrote a couple of years ago called Software-Defined Networking Enhanced Resource Orchestration of Containerized Edge Applications for Industrial Internet of Things. But here, the constraints, the idea was the same. We were using SMT solvers to take constraints of servers like RAM, disk space, and network bandwidth to do an optimization, the load balancing amongst multiple nodes together. And now you can maybe start seeing how this will connect to programming language and array programming languages. And yeah, that's what I'm then doing. I call this my project called Rivi. Calling it an adaptive world computer language is kind of a hyperbolic, but anyway, it's like a GPU-only Rust-based Vulkan scheduler. It's also open source, and I want to integrate it with Beacon later on. But the thing is that now I can use this program to get the capabilities of my laptop and the constraints within it. So it could be something like how much memory do I have on the computer? What are my SIM sizes? Things like this. So just getting like, if you think about the network now, to think about what kind of constraints could you model of these nodes to do the node selection for us. So the this Rivi project is really like combining constraints from Vulkan and given a model of an array operation like a sum reduction, we can get dynamic schedules. So yeah, and I just want to note that like the capabilities to which this approach can be used to perform array operations is a bit hazy right now. But the idea is that if we would have something like this Beacon operation, which is taking 4096 numbers, and it puts a 1 into each one, so it gets a big array, and then it gives us a result, which is actually this thing. But what we can also do is then, the next part, which is, no, now I'm getting a bit hazy here, but the point is that now you could also take these models of array operations given here in an SMT solver. So we can give it an objective that if we have 4 cores, which is the information that we got from here. So it told us that we have 4 queues, which are like cores on the GPU, and then we have these synthesizers and this memory available. Then we can actually think about, we can ask the SMT solver that how should this computation be distributed amongst the individual cores of the computer. And then given that we have 10,000 elements, one result would be this one. So it tells that on the first core you do nothing, on the second you do this, and on the third you do that, and on the fourth you do that. And it gives us like these results in between, and basically tells us that how many steps do we have to run in order to get the final result. So this is now taking on an individual computer basis the idea of constraints to do a static schedule for us. So you can see that how this now, given the NixOS part, I don't have a demo of that yet. I actually couldn't get it to run for certain reasons on my GPU laptop. But then the point is that with the NixOS, you can now create a lens which can expose the physical constraints of each of the devices for the end user laptop like mine, so that I will know where can I find a computer which can do the computation for me, but also how I could slice the program into smaller parts given the physical constraints and capabilities of each device. Yeah, and I think that almost comes a bit to the end of my talk, in the sense that what I really want to have like a takeaway is that given this way to do computation with an array programming language, which is then distributed with an SMT solver, and given this NixOS-based lens to abstract the infrastructure, we can like create or start thinking about new kinds of programming languages which are taking an inspiration from Ethereum and its world computer idea about doing computation in a dynamic and a smart way between different distributed infrastructures. And something that I kind of like want to really note here is that when you're thinking about these distributed networks, then the communication part is arguably the more important part than computing nowadays. Because once you think about like many machine learning models, for example, require one specific GPU to run. So you might have like a very fancy AI model, like a machine learning model, but then you require a certain hardware to do it. And the reason why it's kind of like built like that is that I feel like so many languages nowadays only focus on computing part. And when you kind of like assume that there is no communication between multiple nodes and no easy way to do it, what you will end up doing is doing computation on a single computer rather than spreading it out to a network and somehow magically getting the answer from some node in the end. And so I think that going forward, these new languages should integrate communication and compute together. And what I kind of like was presenting today is a single approach to do it. And my tools were the NixOS and the SMT solver to do it. First, to get the lens, knowing what's the address of each of the nodes where the computers are, but also to get the kind of like the communication link to each of those computers to fetch the constraints which will be used by the SMT solver to figure out how should we compute something. So it's not only a question about what we want to compute. You shouldn't only think about like your arrays and your single algorithm and how it's created, but also the way kind of like how that computation could be divided into smaller parts and how you do the communication, whether it be like in my GPU example with the sum reduction within a single computer or single computer and amongst single cores of that GPU, but also amongst on a higher level between separate computers. And yeah, so I guess like one note here is also this, I actually went to this talk yesterday and there was Tim Barnes-Lee was talking about Web3 and some of his ideas around it and how we could build things on top of the current protocols to address the future problems. But I really think that there still exists a lot of ways we could address the lower end of the stack, not only thinking how we can build the stack upwards, but also how we can address these very basic challenges in our existing protocols like DNS or like IPv4 and 6, in the sense that how we can like programmatically use those existing protocols to query us information to facilitate the new parts on top. So more like thinking about just what bricks to create on top. We could also think that what kind of tooling would be required on the lower stacks of current internet protocols, so that those new capabilities added onto the lower levels could be used to create, let's say, more elegant solutions on top of the stack. So this is like where NixOS and these things are going. It's not only about having the access to different computers, but also like thinking about operating systems in a new way and the communication between these computers. And yeah, it seems like I still have some time. So I have an extra slide, because one thing that I kind of like presented just this higher level architectural or systems approach into doing these programming languages, but I didn't really talk too much about PQN or SMT solvers. But on the other hand, I think I would need maybe I should come here some other time to tell more about those in more particular way. But this nice slides about what is really PQN, or what is APL, or what are array programming languages, then kind of like to figure out that what you can actually do. This is kind of like the constraints in some sense, to also thinking about what kind of computation can you actually even do given these tools. Because PQN and APL work in a rank polymorphic manner, in which the rank is scalar, vector, matrix, cuboid, and the polymorphism comes from Greek and means like many forms of the rank. So basically in PQN and APL, if you do 1 plus 1, 2, 3, 4, you get this result. So here you can see how this structural for loop is constructed for the programmer. So instead of going through its value and telling to add 1 to it, PQN and APL take the structure of the array and kind of like figure out that, well, if you're doing a plus with a scalar added to a vector, then maybe you just want to add a single number to each of the elements. But this also works for higher dimensions. So here what I'm saying is that give me numbers going from 0 to 9, and then reshape it 3 by 3. So give me a matrix which has 3 rows and 3 columns, and then add 1, 2, 3 to each of the rows, and then you get this answer. So in this sense, it's also like very constrained into what kind of computation can you represent in array forms. So that's kind of like, but that's really no real good way to get around it in the sense that if we are talking about the problems about the first and the second point around these proofs and kind of like guarantees about my arbitrary program, not now the smart contract, but any kind of program that I want to run on your computer, how you could know, even though it's not written in a smart contract language, how could you still extract some constraints, some proofs or properties of those programs in the sense of termination and like type checking. And yeah, then there's the last example is that, oh, now you can compose like different things like faults, like some operate, like I'm just trying to like tell you that I feel like one major point in which why these like array programming languages, and maybe this kind of a distributed approach into programming languages has not really been used so far, so yet, is the fact that it requires a completely different mental model from the programmer to think about their problems in a more mathematical and more constrained way, because you're not getting the distribution completely for free. You have to start thinking about your algorithms in ways that those algorithms will be, or those programs will be well defined. And that is very, very hard, but it's also a human problem. So it's a hard problem because people have accustomed to use languages like C and Java and things like this made long time ago and made for a single core computer. But now, since like 2000s or 2005, we started getting dual core CPUs, and then we started to get GPUs with much more cores. And you can now see that if you go to the store and buy an AMD processor, who knows, it might have 64 cores or whatever, and the GPUs probably have 5,000 cores or whatever. So, but the programming languages so far have not really taken that into account, that they are not, like, if you think about it, it's like when you're programming in C or even in Rust, your program by default is single-threaded or single cores. And when you want to do computation on multiple cores, you have to explicitly call like parallel loops or some concurrency primitives to offload the computation on multiple cores. But on the other hand, the array programming languages, which were invented in the 60s as well, so APL, which means a programming language, it's not an array programming language, it just means a programming language. It was that old that the guy who invented it just decided to call it a programming language because there were so few of them at that point. So these languages, because they're so constrained, are based on very like a fundamental and foundational mathematics and things that are well understood, actually translate very well to current day hardware properties and the way that we have constructed the multi-core machines. But that's not really all of it. It's still that to really make it easier to use multi-core computers and a network of multi-core computers, you have to also have the constraints, not on the language level, but on the communication level. And you have to have some programmatic way to extract those constraints from your infrastructure so that you can do this smart language idea of like intelligent load balancing on top of your network. Yeah, I guess I could stop there. I think you might, maybe some people have more questions, but that's about it. Thank you.
Thank you very much. So that's a very insightful talk into APLs, programming language, and also how it can be used as a smart language for a distributed system. Thank you very much. For those that do have questions, you can put it in the chat, or you can also unmute yourself. I'm going to start with a question. So there's a previous slide that talks about how the SMT solver can determine how to use the cores based on the specs of the machine. So yes, from my knowledge right now, for games, something like games or programs, game engines, they have certain algorithms that help the game engine itself determines how to distribute load on the GPU, right? How does an SMT solver do that? Like, is it the same, or how is it? Yeah,
I don't know enough about game engines, whether they use an SMT solver based approach or something more, or more. I think many times, like even if you think about machine learning, many times if you have multiple cores, it's kind of like heuristics based. So you might know that if you have 2 GPUs and you want to split some data that is like very parallel, then the program literally just chunks it into 2 pieces without taking into account the physical capabilities of the computer. And I think there might be another reason why it's probably not SMT based solution, is that there are some quirks about this, which is, first of all, that you have to know how to write SMT clauses or like constraints. So if you look at this on here, you can see that this is in Essence language. So I use something called Savile Row from which is developed in St. Andrews University. And you can see that even though it's using kind of like these quite basic constraints, telling that, oh, you have an input size somewhere and so forth. The problem is that to create these models, you have to know something about the computation beforehand. So it might be kind of non-trivial to maybe do the offloading. And that's one challenge of it. But then there's also this thing right here, and this is in seconds. So these things do not really, at least Savile Row does not scale very well into short-running computations, because to find a solution, any solution, or let's say even an optimal solution, it will take a lot of time. So what is kind of like assumed is that if you use a GPU in a general purpose programming, you will basically have some overhead anyway, because you're probably blocking on that operation for multiple seconds or minutes or hours. And only at that point that the computation takes more than like 1 second, let's say, that's more or less the cutoff point in which you should even take into the consideration of applying SMT solvers to do the distribution for you. But you can see that in some cases, this might be acceptable if you have a device which by basis cannot do the computation in itself, but can do the constraint solving for you. So yeah.
So essentially, for a program that you would like to run in this manner, or like that a smart program that understands, that the machine understands how to distribute, you have to write essentially a SMT solver program for that, so that the machine knows from the program how to run the application nicely. Is my understanding correct?
Yes, that is true, that you have to have the reason why you need to do that is that now if I would plug in here like a AMD or NVIDIA GPU, the constraints, these physical properties about how many cores you have and like what is the SIMD length, so how many operations can you do or how many data points can you compute at the same time, will evolve. So that requires that you have to make it more dynamic than a single kind of like concrete implementation. It has to be a bit more abstract, so that in the case that you have two GPUs, let's say, which have different physical properties, or two CPUs on different machines which have different core counts, to make it so that you can balance it even when the physical properties are not the same, even though they don't have the same amount of cores, requires the fact that there is a more abstract model of that computation in the form of a SMT program. Yes.
Got it. Thank you.
Thanks.
She in the chat asked, is Move the language related in any way to the A programming language?
I don't think so. Move was the smart contract language from Facebook. Do I recall it correctly, or how did this go? I recall remembering something about it, but no, I would say that the current array programming languages, one is at Google, it's called DEX, DEX, and then there's Futhark, and then there's one another from MIT and Adobe, which I cannot really remember. I can put, like, we had a talk series last year in Oxford about the kind of like giving an overall view of everything that there is in what is, they don't really call themselves array programming languages, they call themselves tensor programming languages. But there's some connection, which is that every array programming language that is introduced now, and even I use dependent types to figure out some of these static properties that I give to so to kind of like figure out these computation things. And I think Move, it uses more like, if I remember correctly, it does use linear types, which is a form of, well, you could think about dependence in the sense of linear, like these type systems from that group of family, but those are a bit more limited in the sense that you have Rust, and those are doing more like separation logic to do the multi-core computing rather than using an array programming based approach. So I think the move is foundationally, if I remember correctly, that it's based on separation logic like Rust. Then it uses the separation logic to do the multi-core computation, but it's not exactly what's happening here.
Thank you. Any more questions?
I've got a question. Can I? Hey. Hi. Yeah, Henry here. I was really interested in hearing you talk about this because coincidentally, I actually did my master's research in Oxford as well on decentralized optimization algorithms, right? About basically something like an Adam solver, but breaking up into smaller problems and then distributing it over smaller edge devices. And then those devices are solving their own version of the small problem without knowing the context of the bigger problem, hence, in that sense, preserving privacy, right? And then only compiling the result. And I've got some questions in my head, right? Like the first one is a bit more high level, which is Huawei's DaVinci project, right? And I haven't managed to get too much information online, but most of it seems to be talking about it as like an AI thing. I'm just a bit curious as to why Huawei would use its base stations and its 5G network to kind of like offload computation to users' devices, right? Like what's the motivation behind that, you know? Because people would be I imagine people would be quite unhappy about their phones being used to solve computational problems that are, you know, not something that they specifically requested to do, right? So I'm just curious what is the motivation behind that? Yeah.
Yeah, I think DaVinci project is a bit old terminology. I think the new operating system from Huawei is the concrete implementation of the ideas behind the DaVinci project. There's an article from the Information from many years ago, which kind of like describes it in a more better terms. But the idea is that in this Huawei's vision, I don't think the idea was that like the individual end user devices would be necessarily trading the computation between different end user devices. It was more about Huawei creating the required software so that all the software will be running on the base station. So you would plug in like the GPUs and the servers very close proximity to the base station. So it would then be like an added service to the telecom provider, because you have to see that there's a different, like if you have some company like Deutsche Telekom, or let's say here we have like British Telecom, then they buy that software from the base station providers like Nokia, Ericsson, and then Samsung and Huawei, and they kind of like they provide all the hardware and the software to provide the services to the mobile users. So it was like a way for those telecoms to create their own computing infrastructure so that certain phones could use those services from the base station. So it's like an added value to the internet service provider, because they might be able to offer you within your monthly telecom subscription, like AI computing from the telecoms network, or kind of like computation infrastructure. But
yeah, it's a bit like cloud, right? They're like almost like competing with the cloud in that sense, right?
Exactly. But they are trying to tackle the cloud in a way that the cloud cannot really address it, which is the low latency computation. So they think that when the future will become like a more like a, as they call it, like eyes on, hands off devices, then like the latency will be a big problem with those devices. And with cloud service providers, you might have a long latency to some data center. But if you just plug it into the base station, then the latency to that service is more or less the latency introduced by the kind of like the radio wave coming from the base station to your end user device. But there is a point about Huawei being interested in this, because, and these other companies which produce the full end-to-end solution, to like telecom, which is doing like Samsung, for example, and I guess Nokia to some extent, which are doing the phones and the base stations together, because then they don't have to compete with the features provided by, like they don't have to make a phone which is better than, let's say, Apple's iPhone, because the computation is partially coming from the, like you're not competing whether you have a better phone than with Apple, but you're competing with the fact that whether your internet service provider is created on Huawei's or Nokia's or Samsung's network. So it could, so basically if you get a Samsung phone and your internet service provider is using Samsung base stations, then you get extra features on your phone. So your phone becomes better or cheaper to produce because it's kind of like baked into your telecom subscription.
Yeah, I can it's much clearer to me now because I do machine learning and edge compute as well, right? And it's not a question about whether or not there is compute resources, right? Because AWS, all these clouds have compute resources. The problem is utilizing it, right? And availability, right? Like what you say, latency, and having to move data all the way from from Malaysia, which doesn't really have those data centers, all the way across the US, and it's only certain chips are only available in certain parts of the US as well, not in Singapore, and it's just a mess, right? In terms of the networking and the bandwidth, right? It's not even a question of like there's a compute; it's just there's compute, but I just can't use it, right?
Exactly. So that's kind of like where I want to like highlight with the communication thing is that when you have the SMT solver, you have to also think about that the SMT solver doesn't have to necessarily be that the constraints are coming just by the physical constraints of the device. The SMT solver could also take any arbitrary constraints about the network. So you could model in your bigger SMT model like network bandwidth limitations and latency things, so that you could like start addressing the communication and the data moving part rather than just thinking about compute. Yeah.
Right. So it's a language. It sounds to me like a language that is a bit more catered towards ensuring that distributed computing and also networking is managed well, right, and efficiently.
Yes.
I'm just wondering, like, is it a specific type of programming language such that it's not necessarily Turing complete, for example?
Yeah, so I work on Turing incomplete languages. So for you to be able to think about the program slicing, it usually means that you have to know something about the program and things like whether to really know that how you can slice some array operation into smaller pieces. It would be nice to know whether that operation will even terminate or something like that. So yeah. I think there might be like but it can get hazy because you think that you could take, like, I don't think that everyone will be necessarily using a language like this for everything, but they might be programming in Python, and then they have a part in Python which uses this tooling. So it's kind of like now you use Python and then some part of the program uses GPUs. So I think the same way is that maybe there's a fragment in your overall program that would benefit from this kind of approach. And then it doesn't really matter whether it's a Turing complete language, because if there's a Turing incomplete fragment in that program, then that can be distributed.
Yeah, inline code, like how we do for SQL statements as well in Python, sprinkling that, and C++ statements as well in Python. Yeah.
Exactly.
Gotcha. Cool stuff. Yeah.
Thanks.
Thank you. There's a question in the chat. So Aslak is asking, how would BQN know whether to distribute its compute on CPU cores or the GPU or both? Isn't it the OS that knows which resources are free at any time?
Yeah, so that's like where I want to go. So BQN currently, cPQN, which I used on these slides as an example, runs only on CPU cores. But I haven't got that around it because it's a bunch of software engineering work. But I want to do it so that given certain operations, there would be like an added interpreter on top of cpqn, which uses cpqn to do most of the operations, but when it detects that there is a big array operation, it would be probably be a combination of some basic heuristics, but also then the features that could be queried with something like NixOS to do the offloading to the GPU, like in case-by-case basis, and then continuing, like it would basically get the pointer from C, and now that I'm writing the GPU stuff in Rust, then the Rust program does the thing, returns a pointer, which is given to cpqn, and then it continues. So that's something I have not quite, I don't think there's an elegant solution to that, but I think there's many approaches and tools to iterate over.
Got it. I think we have like 4 more minutes, so I think we can take 1 or 2 more questions. So for anyone who wants to ask a question, you can again do it in the chat or yes, this voice up. I personally have 1 more questions.
Yeah,
I have a lot of questions actually, but you know.
yeah. Just let me know later on. So
Yeah,
you can send me email or whatever if you have more questions or want to talk in more depth, like any one of you.
Yeah, me too. But I think I would just like drag it too long.
Yeah.
I mean, yeah, I think in the case, I think I'll just talk to you later about this. So is there any more questions from the audience? If not, I think that's a wrap.
Right. Thank you.
Yep.
I appreciate the
thank you
chance
for
to
coming.
talk. Yeah, great questions. It's nice to see that other people are also interested in the same stuff, so I don't feel so crazy myself.
I did a master's on it, so I guess I'm crazy too, I guess.
Great.
Dedication. Okay. So thank you everyone for coming. I'll pass it to Kim.
Yeah, now thanks everyone for coming. So now I'm going to stop the recording.